In this video, we'll begin our discussion of what's called a directional derivative. Um, we have talked about several occasions already, talking about that in three space we are going to have multiple directions of a derivative, right? Imagine yourself standing on the hillside on the screen. I'll even put a dot there. Imagine you're standing there. Each direction, if you go up, you have a positive slope going up the hill. You could go down the hill, you could go to the left, you could go to the right, you could go at a 30-degree angle, you could go at all these different angles, meaning that we have an infinite number of derivatives given a point on a surface. In the motivation assignment, the beginning assignment, whatever it may be called for your course, when you're watching this video, I had you guys go through a method of finding a slope in three space and what that may look like, and had you think about that. In this these next 2 pages, they're going to use that idea to show you the equation or theorem for what we call a directional derivative, which is going to be a derivative of a line going in a certain direction. Given a slice, right? Let's take a look at our picture down here. You can see that we could say, hey, in that direction of this vector right here, PQ, right, going in that direction, we can find a slope of that point in that direction. So this formula is going to help us do that. I'm not going to go through the theory with that. I let you guys kind of play with the idea with the beginning assignment. If you would like to read it, I have it here in the notes for you. It's not too bad to follow along. The definition of a directional derivative is about the same as definition of a derivative, just that inside part there. And I'll let you read why that looks like that. Where we are going to land in our video is right here. Right? Please ignore the theorem number. I don't know if our book will line up to that depending when you are watching this video. Not too important. All right, this directional derivative, this will give me the derivative given so I have a function f that is in terms of x and y. Then we also have a unit vector because we have to know what direction our derivative is going to be in. So notice our unit vector must look like this. Now, key word here, unit vector, right? The unit being the key word. It has to be a unit vector. So sometimes they're going to give you a vector and they're going to say, find the directional derivative in the direction of this vector. And you will need to make it a unit vector for this formula to work out. So notice that when we plug in everything, there's no i's and j's. It's just a number. It literally is the slope of the tangent line that follows that vector at that point. So we have a couple things here. We have the partial of x times cosine, right? That checks out, right? Partial or x and cosine typically go together. Y and sine typically go together. And then there's the proof to sum up that whole definition for us. We're going to leave it the way it stands and get into doing some examples. All right. So consider this example. I wrote the definition up there, and what u means in this case, find the derivative of this function at the point 1, 2 in the direction of the vector that makes an angle of pi over 6 with the x-axis. Okay, so I'm going to draw a picture just to kind of help myself out. I know I have a vector that goes like that, and the angle in between is a pi over 6. All right, and we're trying to find the derivative that goes in that direction from the point 1, 2. Okay, so if we're building this, first thing let's do is build our vector, and it's going to be a unit vector. Right, we build that, and this is nice and set up for us. Cosine of the angle. So cosine of pi over 6, sine of pi over 6. Now, they may not give you theta, and if they don't, that's okay. You can just use the coordinates, just make sure it's a unit vector. If it's not a unit vector, make it a unit vector. Okay, so we have that. So a unit vector is going to be, cosine of pi over 6, that is going to be radical 3 over 2. Sine of pi over 6 is 1 over 2. Right, so we know it's in that direction. I also need my partial derivatives of f. So f partial with respect to x is 3x squared minus 4x. Partial of the function with respect to y is going to be 3y squared. So if I want the directional derivative, I'm just going to write it in general right now, of that direction of our function, All right, that is going to be 3x squared minus 4x times radical 3 over 2 plus 3y squared times 1 over 2. Notice there are no i's and j's. Should be circular or parentheses, not a bracket there. And if I want the point, okay, the point was, just plug it in. What was it? It was 1, 2. Okay, so plugging in 1 here. Sorry for the scrolling there. Sometimes it gets out of control. 3 minus 4, it's plugging in 1 times radical 3 over 2. Plus, okay, and I'm plugging in 2 here, so I got 3 times 2 squared times 1 half. All right, that is going to be a negative rad 3 over 2. Plus 2 squared is 4 times 3 is 12 times 1 half is 6. I think that's a great answer. It's an exact answer. I could go and get a decimal. That is the slope of the tangent line, right? Or tangent, I guess, the derivative of that, the directional derivative, the tangent line that slices along this vector. So it does make sense to call it a tangent line because we're living in a plane, right? But along that, from the point 1, 2, it goes the next going, and it looks like it's an increasing. It's positive. It's greater than 0. It's going uphill for 1 unit up, right? Whatever the derivative means in that case, 1 step unit.